For an object defined by its impossible cold by an eon-spanning journey through the absolute zero of interstellar space, it arrived with a secret fire. It didn't announce itself with the brilliant flourish of a typical comet, a predictable celestial peacock fanning its tail of ice and dust. Instead, it slipped into our solar system like a phantom, a whisper of motion against the velvet backdrop of eternity, carrying a paradox within its core that would challenge the very foundations of our understanding of matter itself. This is the story of 3I, Atlas, the third interstellar object ever detected, a messenger from a forgotten star that brought with it not an answer, but a profound and unsettling question. Before you can even begin to comprehend the anomaly it represents, you must first attempt to grasp the journey it undertook. This was not a trip measured in years or even centuries. This was a pilgrimage of deep time, an odyssey so vast it reduces human history to the blink of an eye. Imagine a solitary fleck of cosmic dust born in the swirling, chaotic nursery of a star system. You will never know a place with a sun of a different color, orbited by planets of unimaginable form. This fragment was likely ejected from its home in a violent gravitational dance, flung into the void by the pull of a giant planet, a gravitational slingshot that severed its connection to its parent star forever. From that moment on, it became a wanderer, a ghost ship sailing the silent dark ocean between the stars. For millions, perhaps hundreds of millions of years, it drifted. Its universe was one of profound emptiness, a realm punctuated only by the faintest whispers of reality. It tumbled through the thin, cold hydrogen gas that permeates the Milky Way, a tenuous fog that does nothing to warm the soul-crushing chill. It was bombarded not by sunlight, but by high-energy cosmic rays, the shrieking subatomic shrapnel of distant supernovae particles accelerated to near the speed of light that tattooed its surface with aeons of radiation damage. The light from nearby stars would have been nothing more than sharp, distant diamonds, offering no warmth, no comfort, only a reminder of the homes it could never reach. Think of the cold, not the bracing cold of an earthly winter, but a perfect, absolute stillness where molecules themselves nearly cease to vibrate. A cold that seeps into the very bonds of matter, locking it into a state of suspended animation. Its path was a silent ballet of near misses and distant influences. It would have felt the ghost of a touch from the gravitational tides of colossal molecular clouds, those dark, star-forming nurseries where new suns ignite. It may have passed through the wispy, ethereal remnants of a stellar explosion that occurred 1,000,000 years before its arrival, a phantom limb of a long-dead star. For every year of its journey, it travelled 60 trillion miles further into the unknown, a silent, frozen witness to the galaxy's slow and majestic turning. It carried with it the chemical signature of its birthplace, a pristine, uncontaminated sample of the raw materials that build worlds elsewhere. It was a time capsule sealed not by metal and glass, but by the unfathomable cold and vacuum of the interstellar medium. We look out at the stars and wonder what they are made of, what kinds of planets circle them. This object was a direct delivery, a piece of that puzzle, gift wrapped in the darkness of space, hurtling directly toward us. And then, after an eternity of solitude, it felt a new sensation, a gentle, persistent, and ever-increasing pull. At first, it was infinitesimally weak, the barest hint of gravity's touch across light-years of empty space. But this touch was different. It wasn't the fleeting influence of a passing star or a diffuse nebula. This was a cosmic anchor, a deep and powerful gravity well that was reeling it in. It was the gravitational field of our sun. Having flown for ages through the galactic wilderness, our interstellar traveller had by sheer chance stumbled into our celestial backyard. It was falling, accelerating faster and faster, leaving the blackness of the void and entering the warm, sunlit confines of a home that was not its own. Its arrival was not greeted by trumpets. It was noticed as a faint, almost imperceptible smudge of light, captured by the unblinking robotic eyes of the Asteroid Terrestrial Impact Last Alert System, Atlas, our planetary defense network in Hawaii. These telescopes are our silent sentinels, our watchtowers on the cosmic shore, tirelessly scanning the heavens every night for anything that moves. They are programmed to find the near-Earth asteroids, the chunks of rock and ice native to our own system that might pose a threat. But this smudge was different. It didn't move like one of ours. Astronomers plotting its trajectory saw something that made their hearts race. The object's path was not a gentle closed ellipse, the familiar repeating loop of a planet or a local asteroid forever bound to our sun. Instead, its trajectory was a wide, sweeping, open-ended curve, a hyperbola. In the language of orbital mechanics, this is a declaration of independence. It meant the object was moving so fast, possessed such an incredible amount of kinetic energy, that our sun's immense gravity was not a chain but a temporary diversion. It was a cosmic bullet that had been fired from deep space, and it would curve around our star only to be flung back out into the interstellar darkness, never to return. This was the irrefutable proof, the celestial fingerprint of an outsider. It came from beyond. It was only the third such visitor we had ever confirmed, a priceless opportunity to study a piece of another solar system up close. The astronomical community buzzed with excitement. Telescopes across the globe and in orbit above it swiveled to get a look. Based on our previous encounters with interstellar wanderers, we thought we knew what to expect. The first, the bizarre cigar-shaped Oumuamua, was a mystery, a dark, inert rock that tumbled strangely and accelerated for reasons we still debate. The second 2I, Borisov, was far more obliging. It behaved exactly like a classic comet from our own Oort cloud. As it approached the sun, its ices began to sublimate, erupting from its surface and enshrouding it in a beautiful glowing cloud of gas and dust called a coma. This coma, pushed back by the solar wind, formed a glorious tail. Borisov shone brightly, reflecting sunlight from its newly formed atmosphere, giving us a spectacular show and allowing us to analyze the chemical composition of its vaporizing ices. So for 3I, Atlas, the expectation was clear. As it plunged closer to the sun, a point in its orbit known as perihelion, it should have woken up. The sun's intense radiation should have acted like a celestial blowtorch, peeling back its ancient frozen layers. We anticipated the first signs of outgassing, the telltale spectral signatures of water ice, carbon monoxide, or other volatile compounds turning to gas. We expected it to brighten dramatically its surface, transforming from a dark, irradiated crust into a brilliant mirror of freshly exposed ice. We had our cameras ready, our spectrographs primed, waiting for the performance to begin. We were waiting for a comet, but 3I, Atlas, remained stubbornly, unnervingly silent. As it rounded the sun, it failed to produce any significant coma. There was no tail, no brilliant shroud of gas and dust. It remained a simple, unresolved point of light, a frustratingly shy visitor refusing to reveal its nature. This was puzzling, but not unprecedented. Perhaps it was more like Oumuamua, an inert rocky body with very few ices to begin with, an interstellar asteroid rather than an interstellar comet. This would make it less spectacular, but still a scientifically valuable object. It would simply be a dark, reflective chunk of rock from another star. We pointed our most powerful instruments at it, trying to measure the faint light it bounced back our way, hoping to determine its size, its shape, and what its surface might be made of. And that is when the mystery deepened into a profound physics-defying enigma. The data that came back made no sense. It was dark, impossibly dark. Its albedo, the measure of its reflectivity, was shockingly low. Most comets and asteroids in our solar system reflect a reasonable amount of sunlight, like asphalt or coal. 3I, Atlas, was reflecting almost nothing. It was darker than any known natural object in our solar system. It was like a hole in space, a patch of absolute blackness against the star field. But that wasn't even the strangest part. The true anomaly came not from the light it was reflecting, but from the heat it was emitting. Using infrared telescopes, which see the universe in terms of thermal energy, astronomers measured the object's temperature. As it soaked in the intense radiation from the sun, it should have heated up and re-radiated that energy back into space as heat glowing faintly in the infrared spectrum. The physics is straightforward: energy in must equal energy out. The object should have reached a predictable equilibrium temperature based on its distance from the sun and its presumed reflectivity. But the numbers were wrong. They were profoundly, fundamentally wrong. 3I, Atlas, was far warmer than it should have been. It wasn't just passively absorbing and re-radiating energy. It was actively, bizarrely hoarding times it. Somehow this object was drinking in the torrent of solar radiation and holding onto it. The light that fell upon its surface was not bouncing off. It was being captured, its energy converted to heat with an efficiency that defies our current models of planetary science. Imagine standing in the bright summer sun wearing a black velvet cloak. You expect to get hot, but imagine that cloak somehow becomes a thermal sponge, not only absorbing all the light but also preventing the heat from escaping, growing hotter and hotter in a way that seems to violate the natural laws of cooling. This is what we were witnessing from trillions of miles away. The object was absorbing solar energy, yet its thermal radiation signature, the heat it was giving off, was behaving in a completely unexpected way. It was a thermodynamic puzzle of the highest order. This single observation shattered our neat categories. It wasn't a comet, as it had no coma. It wasn't a simple asteroid, because asteroids don't behave this way. It was something else entirely, a new class of celestial object whose properties we had never imagined. The implications are staggering, and they ripple outward, touching every aspect of our search for life and our understanding of the galaxy. This object is a building block of another world. The fact that it is so fundamentally different from the building blocks of our own world, our comets, our asteroids, is a revelation. It suggests that the chemistry of planet formation around other stars could be wildly, beautifully, and perhaps dangerously different from our own. What kind of material can do this? What substance forged in the heart of a distant protoplanetary disk can absorb light so perfectly, yet manage its thermal energy in such a peculiar fashion? Is its surface coated in some exotic, hyperporous material, a kind of cosmic aerogel that traps photons, like insects in amber? Could it be composed of some strange, fractal-like aggregate of organic molecules? A structure that dissipates heat into its interior instead of radiating it away? Or are we witnessing a phenomenon so alien that we lack the vocabulary, the very physics to describe it? This is no longer a simple question of astronomical classification. It has become a question of fundamental materials science, of exotic chemistry, and of the diverse ways that planets can be born across the galaxy. 3I, Atlas, has become more than a visitor. It is a messenger carrying a cryptic note we are struggling to decipher. It flew past us, a fleeting opportunity that has now passed as it recedes back into the infinite night from which it came. But it left behind a wake of consternation and wonder, a trail of baffling data that has sent theorists back to their blackboards. It has shown us that our assumptions about how worlds are made, based on the single data point of our own solar system, may be tragically incomplete. The universe is not just stranger than we imagine, it may be stranger than we can times imagine. To solve this riddle, to understand what this object truly is, we must now become detectives. We must sift through the faint photons it grudgingly returned to us, dissecting their every property. We must analyze the spectrum of that faint thermal glow, searching for clues in the language of light itself. What forgotten stellar forge could create such an enigma, a thing that drinks the light and holds it like a secret? What process could assemble matter in a way that so thoroughly breaks our expectations? The answer lies hidden in the handful. 2 of measurements we managed to take as this phantom slipped through our grasp, a puzzle that promises to rewrite the story of how star stuff becomes a world. The investigation has just begun. What if the greatest messages in the universe are not carried on waves of light or sound, but are delivered by hand? For millennia we believed our solar system was an island, a self-contained cosmic terrarium, sealed off from the vaster, wilder galaxy beyond. The heavens above, while immense and mysterious, were fundamentally times ours, asterisk. The planets, the asteroids, the comets, they were all members of our celestial family, born from the same swirling cloud of gas and dust as the earth beneath our feet. We studied them as a way to study ourselves, to understand our own origins. We thought we knew the rules of this place, the physics that governed the silent dance in the dark. And then a messenger arrived, and it taught us that we were not on an island at all. We live on the shore of an infinite ocean, and the tide was finally coming in. To understand the revolution, you must first understand the old world, the celestial order we took for granted. For centuries, our most ethereal and breathtaking visitors have been the comets. They were not born in the warm, well-lit inner solar system, but were relegated to its most distant, frigid frontiers. Imagine a sphere of unimaginable size encasing our entire solar system in a shell of deep frozen relics. This is the Oort cloud, a dark reservoir holding trillions of sleeping cosmic beasts. It is a place so far away that the sun is just the brightest star in the sky, its warmth a forgotten memory. Here in the crushing cold and the profound dark, time itself seems to stand still. These are the remnants of creation, the leftover bricks and mortar from the construction of our planetary home, hurled into the void 4.5 billion years ago. They are dirty snowballs, yes, but that simple name belies their profound nature. They are archives of primordial water, cosmic dust, and organic molecules, the very ingredients of life locked in a cryogenic slumber. For uncounted eons, a comet might drift in this silent kingdom, an inert ball of ice and rock. But the galaxy is not a tranquil place. A passing star, its gravitational wake rippling through the dark, might give one of these slumbering bodies a gentle, fateful nudge. And so begins a journey of staggering scale, a slow, inexorable fall, a pilgrimage lasting millions of years from the cold, outer darkness toward the fire at the heart of our system. For almost the entirety of this descent, nothing happens. It remains a frozen, silent traveller, invisible to us, a ghost slipping through the planetary orbits. But then, as it crosses the frost lines somewhere out past the orbit of Jupiter, a magnificent transformation begins. The distant sun, once a feeble point of light, becomes a source of power, a celestial blowtorch. Its faint warmth starts to caress the comet's surface, and the ancient ices frozen since the dawn of time begin to stir. They do not melt. In the vacuum of space, they sublimate, turning directly from solid ice into gas. This process is the comet's grand awakening. The surface erupts in jets and geysers of vapor and dust, spewing the material of its very being out into the void. This cloud of gas and debris, this temporary atmosphere, is called the coma. It can swell to become larger than a planet, a ghostly shroud enveloping the tiny solid nucleus within. And as the comet plunges deeper, closer to the sun, the real spectacle ignites. The solar wind, a constant stream of charged particles flowing from our star, catches this expanding coma like a gale catching a sail. It pushes the gas and dust away, sculpting it into vast luminous banners that stretch for millions of miles across the sky. This is the comet's tail, its signature flourish, its declaration of arrival. It is a spectacle of pure reflection. The comet itself, the nucleus, is one of the darkest objects in the solar system, often blacker than coal. It does not generate its own light. The breathtaking beauty you see, the glowing apparition that has inspired both fear and wonder throughout human history, is nothing more than sunlight glinting off a veil of its own discarded dust and ice. It is a passive performance, a mirror held up to the sunday. This was the fundamental unchallenged rule. Comets are icy wanderers. They come, they perform their sun-powered spectacle of reflection, and they either swing back into the darkness or are consumed by the fire. They were all times our time's comets, until they weren't. On October 19, 2017, an automated telescope in Hawaii, part of the Pan-STARRS Sky Survey, flagged a faint, unassuming point of light. The system's job is to scan the heavens for asteroids and comets, particularly those that might pose a threat to Earth. It finds thousands of new objects a year, their orbits log, their paths predicted with Newtonian certainty. But this object was different. It refused to conform. As astronomers around the world began tracking it, they realized its trajectory was wrong. Every comet, every asteroid we had ever seen was on an elliptical or circular path, gravitationally tethered to our sun, a cosmic anchor holding it in our system. They are all boomerangs destined to return. This new object, however, was on a path that was wildly, unambiguously hyperbolic. It was not looping around, it was just passing through. It was moving at a blistering 196,000 miles per hour, a speed so immense it could not possibly be bound by our sun's gravity. It was a cosmic bullet fired from the depths of interstellar space. It had been travelling for millions, perhaps billions of years across the gulf between the stars. For the first time in history, we were staring at a visitor from another solar system. We named it Oumuamua, a Hawaiian word for a messenger from afar arriving first. The name was perfect, for it had brought with it a revolution in thinking and a profound, unsettling mystery. As our greatest telescope strained to get a better look before it vanished back into the void, the strangeness only deepened. Based on our understanding, an interstellar object was most likely to be a comet ejected from its own nascent star system. We expected to see a coma, a tail, the familiar signs of sublimating ice. But Oumuamua was utterly inert. There was no gas, no dust, not the faintest hint of an outburst. It was just a dark, silent object tumbling end over end on its journey through our home. Its colour was a deep, dark red, consistent with being bombarded by cosmic rays over an immense span of time. And its shape, inferred from the radical changes in its brightness as it spun, was unlike anything we had ever witnessed. It was not a sphere. It was something extraordinarily elongated, perhaps 10 times longer than it was wide. A cosmic needle, a celestial cigar, an artifact of some unknown celestial mechanics. But the greatest puzzle was yet to come. As Oumuamua rounded the sun and began its exit journey, astronomers noticed something that defied explanation. It was accelerating. It was pushing away from the sun with a tiny but persistent non-gravitational force. It was moving faster than gravity alone could account for. For a normal comet, the answer would be simple outgassing. The jets of sublimating ice act like tiny rocket thrusters, giving the nucleus a gentle, unpredictable push. But Oumuamua had no visible outgassing, no coma, no tail. So, what was pushing it? The scientific community erupted in a storm of debate and speculation. Was it venting some kind of exotic gas our telescopes couldn't detect, like pure hydrogen ice? Was it an object of impossibly low density, a cosmic snowflake being pushed by the subtle pressure of sunlight itself? The questions were tantalizing. The data was sparse, and the object was already gone. A fleeting whisper that had passed in the night. Oumuamua left us with a cosmic riddle, a haunting sense that the universe beyond our doorstep was far stranger than we had ever dared to imagine. It was a messenger, but the message was written in a language we could not read. For 2 years, the mystery lingered. Was Oumuamua a once-in-a-lifetime freak, a statistical anomaly so rare we might never see its like again? Or was it the first drop of rain in a coming storm, a sign that our solar system is routinely visited by travelers from other stars? The answer arrived on August 30th, 2019. This time, the discovery was not made by a giant state-of-the-art observatory, but by an amateur astronomer in Crimea named Gennady Borisov, using a telescope he had built himself. He spotted a fuzzy object with a short tail, and like the professionals, he noted its trajectory was all wrong. The global astronomical community scrambled, confirming his observations within days. The world had its second confirmed interstellar visitor. And this one, named Two-Eye, Borisov, in his honor, was everything Oumuamua was not. It was a revelation, but a comforting one. As it drew closer to the sun, it behaved exactly as a comet should. It developed a magnificent glowing coma and a long streaming tail. It looked, for all intents and purposes, like a classic comet from our own Oort cloud. The mystery of Oumuamua's acceleration was suddenly placed in stark relief. Borisov was clearly being pushed by conventional outgassing, its jets of water vapor and dust visible for all to see. When our telescopes analyzed the light from Borisov's coma, we found familiar molecules, water cyanogen, but also a surprisingly high abundance of carbon monoxide. This offered a stunning glimpse into the chemistry of its home star system, a chemical fingerprint of a place light years away. Borisov was the proof we needed. Interstellar objects were not impossibly rare. They were real, they were traversing our system, and they looked by and large just as we expected them to. A collective sigh of relief went through the astronomical world. Oumuamua was the outlier, the bizarre exception. Borisov was the rule. It became our new template for what a typical interstellar comet should be, an icy, dusty body that upon entering our solar system would put on a spectacular reflective show as the sun awakened its frozen heart. This new understanding created a framework, a set of expectations for the next visitor that would inevitably arrive. We were now prepared. We knew what to look for. We believed we finally understood the nature of these messengers from the dark. We were wrong. The next alert came from the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a robotic survey designed for the same purpose as Pan-STARRS. Another faint speck of light, another impossible trajectory. By now, the procedure was almost routine. The orbital mechanics were calculated, the hyperbolic path confirmed. The third interstellar interloper, designated 3I Atlas, had been found. A palpable excitement electrified observatories across the globe. Here was another chance, another precious sample delivered to our doorstep from a distant, unknown star. The key question on everyone's mind was, which kind of visitor would this be? Would it be another baffling inert enigma like Oumuamua, offering us a chance to finally solve the puzzle of its silent acceleration? Or would it be a sibling to Borisov, a conventional but still profoundly exciting interstellar comet, allowing us to catalogue the chemical diversity of other stellar nurseries? Every available instrument, every telescope capable of getting a fix, pivoted toward this new point of light. The first wave of observations began to trickle in, painting a preliminary picture. Initial reports showed no coma, no dust, no tail. Like Oumuamua 3I, Atlas appeared completely inert as it made its approach. The excitement intensified, leaning toward the tantalizing possibility that we had found another object of that strange and mysterious class. Perhaps this time we would catch it early enough with better instruments to see the subtle outgassing that had eluded us before, or confirm its bizarre elongated shape. The world's astronomers were holding their breath, ready to test the wild hypotheses born from Oumuamua's fleeting visit. The next step was to gather thermal data to measure the object's temperature and determine its reflectivity, its albedo. This was a standard measurement, a routine piece of the diagnostic puzzle. Telescopes sensitive to infrared radiation, which see heat rather than visible light, were trained on the visitor. The data began to stream back to Earth, and as scientists processed the first thermal readings from 3I, Atlas, a quiet, chilling disbelief began to spread through the community. The numbers didn't just break the rules, they were impossible. The object was not reflecting the sun's light as a dead inert rock should. It was not cold as an icy body so far from the sun must be. Against every known law of thermodynamics, for a cometary nucleus, against every model of celestial objects we have ever created, 3I, Atlas, was registering as inexplicably unnaturally warm. It was behaving as if it was somehow capturing and storing the energy from the sun, rather than letting it bounce off its surface. The data suggested an object that was not a mirror but a sponge, not a passive reflector but an active absorber. The mystery was no longer about a strange shape or a subtle push. This was a fundamental violation of physics as we know it. The messenger had arrived, but it was not carrying a note we could not read. It was carrying a fire we could not comprehend. The question was no longer simply what it was, or where it came from. The question that would consume us, that would challenge the very foundations of our understanding of matter and energy in the cosmos, was how was this silent visitor from the stars drinking the light undefined? And so another ghost from the interstellar dark had drifted into our celestial home. After the bewildering passage of Oumuamua and the familiar visit of Borisov, humanity's new sentinels, the automated eyes of the Atlas survey were primed. They scanned the heavens with a tireless digital gaze, not for the grand, slow waltz of the planets, but for the faint, fleeting whispers of intruders. On a cold, clear night, amidst a torrent of data streaming from a mountaintop in Hawaii, one of those whispers was finally heard. It was not a shout, not a brilliant flare of discovery, but a barely perceptible smudge of light, a tiny smear against the velvet black, moving with a purpose that was not our own. The system flagged it, an anomaly. A single ghostly pixel behaving in a way it should, not tracing a path that defied a simple sun-bound explanation. This is the humble beginning of so many cosmic stories. An automated alert, a pre-dawn email to a bleary-eyed astronomer, a quick check against the star charts. At first it was designated with a provisional, almost anonymous label, a mere catalogue number for a potential near-Earth object. But as observatories around the globe began to pivot their immense mirrors toward this faint traveler, a new narrative began to write itself, one observation at a time. Each new data point, each new measurement of its position was fed into the world's most powerful computers, which worked to connect the dots. They were trying to chart its past and, more importantly, predict its future. The initial calculations were tantalizing, suggesting an orbit that was unusual, highly inclined, stretching far out into the frozen wastes of the solar system. For a few frantic days, it was treated as just another long-period comet, a prodigal child of our own sun returning after a million-year sojourn. But the more data we gathered, the more the orbital solution refused to settle into a familiar elliptical path. The numbers were stubborn. They kept pointing to a trajectory that was not a closed loop, but an open curve, a hyperbola. This was the mathematical signature of a visitor, an object not gravitationally shackled to our star. It was moving too fast, its momentum a testament to a journey begun somewhere else in the cold and the dark around a star we have never seen. The International Astronomical Union confirmed it, bestowing upon it the formal designation 3I, Atlas, the third confirmed interstellar object. A thrill coursed through the astronomical community. We had another chance. Another precious opportunity to study a pristine artifact from another star system, a direct sample of the building blocks of a world light years away. Based on the precedent set by Borisov, the second visitor, the expectations were clear. We anticipated a comet, a magnificent, untamed interstellar comet forged in a protoplanetary disk alien to our own, now set to awaken spectacularly as it neared our Sunday. The world's telescopes trained upon it, ready to witness the show. We were waiting for the first signs of life, the telltale shimmer of a developing coma as the sun's warmth began to touch its ancient frozen surface. This is the grand transformation for any comet. For billions of years, it is an inert rock of ice and dust, a dead thing tumbling through the vacuum. But as it approaches a star, it is reborn. The frozen gases, water, carbon dioxide, ammonia, are supposed to feel that stellar breath and begin to sublimate, erupting from the nucleus in violent jets. This process, this celestial exhalation, creates the gossamer shroud we call a coma, and eventually the magnificent tail that stretches for millions of miles. This is what a comet does. It is the core of its identity. We were watching 3I, Atlas, waiting for it to follow the script. The first tool we use to chart this awakening is one of astronomy's most fundamental, the light curve. It is a simple yet profoundly revealing concept. You measure an object's brightness over time. For a comet, this curve tells a dramatic story. As it gets closer to the sun and its icy engines ignite, its brightness should soar, not just because it's getting nearer, but because the expanding cloud of gas and dust in the coma acts like a giant mirror reflecting vastly more sunlight back at us. This light curve should be punctuated by unpredictable flashes and outbursts, the signatures of fresh vents of ice being exposed to the sun, creating sudden dramatic increases in brilliance. It is the chronicle of a dynamic, violent, and beautiful process. Astronomers began plotting the light curve for 3I, Atlas taking measurements night after night, and as the points began to appear on the graph, a deep, unsettling quiet began to descend upon the observatories. There was no soaring curve, there were no dramatic outbursts. Instead, the data points formed a nearly straight, gently rising line. The object was getting brighter, yes, but only by the precise, predictable amount you would expect from any inert rock simply getting closer to us. It was as if we were watching a cannonball approach, not a firework. The data was clean, precise, and utterly profoundly wrong. The cometary engines, the spectacular jets of sublimating ice that should have been firing, were silent. This cosmic messenger was flying under a flag of absolute radio silence, its performance a flat, monotonous hum where we expected a crescendo. The first seeds of confusion were sown. Perhaps it was just a slow starter. Maybe its surface was covered in a thick, insulating crust of dust that needed more time, more heat to breach. It was still far out beyond the orbit of Mars. Patience, the community counseled itself. Patience, the real show would begin soon. But as our telescopes peered deeper, another more powerful tool was brought to bear: spectroscopy. If a light curve is an object's biography, its spectrum is its soul. By capturing the faint light from 3i, Atlas, and passing it through a prism-like instrument, we could shatter it into its constituent colors, a rainbow smeared across a digital sensor. Within this rainbow are hidden dark lines, gaps where specific colors are missing. These are absorption lines, a unique, unforgeable fingerprint left by the chemical elements on the object's surface. Each element, each molecule, absorbs light at its own characteristic wavelengths. By reading this cosmic barcode, we can determine precisely what an object is made of. For an awakening comet, the spectrum should have been rich with information. We expected to see the distinct signatures of water ice, the telltale lines of cyanogen and diatomic carbon, the classic chemical markers of cometary activity. We were looking for the ingredients of a primordial soup from another star. The first spectra of 3i, Atlas, began to trickle in from the largest telescopes on Earth, instruments capable of capturing and dissecting the light of just a handful of photons arriving from the depths of space. The data was processed, the noise was filtered out, and the resulting graphs were displayed on screens in control rooms from Chile to Arizona, and the silence that had begun with the light curve deepened into a state of collective scientific shock. The spectrum was nearly featureless. It was a smooth, gently sloped line, almost devoid of the chemical fingerprints we were so desperately searching for. There was no clear signature of water ice. No hint of the complex organic molecules we had seen in other comets. It was a canvas painted in a single monotonous shade of reddish-brown, offering up almost no information at all. This was more than just unusual. It was deeply paradoxical, an object on a cometary orbit, yet showing none of a comet's defining characteristics. It was like finding a dolphin that couldn't swim or a bird without feathers. The featureless spectrum pointed to a surface that was remarkably uniform and most critically incredibly non-reflective. This led the investigation to the next crucial parameter, its albedo. Albedo is simply a measure of reflectivity. An object with an albedo of 1 like a perfect mirror reflects all the light that hits it. An object with an albedo of 0 is a perfect black body, absorbing everything. Fresh snow has an albedo of around 0.9. The Earth's is about 0.3. A typical comet, often described as a dirty snowball, has a surprisingly low albedo around 0.04. Its surface is coated in dark carbonaceous dust, making it blacker than asphalt. This is already remarkably dark. We thought we understood the lower limits of reflectivity for objects in our solar system. To calculate the albedo of 3i, Atlas astronomers had to perform a careful balancing act. They measured its brightness in visible light, the amount of sunlight it was reflecting. Then they used its trajectory to calculate its size based on the assumption that it was a typical comet. When they put the numbers together, the result was nonsensical. For it to be as dim as it was, it had to be impossibly small, or it had to be made of something that simply did not want to reflect light. As more data refined its size estimates, the horrifying truth about its albedo began to emerge. The number they calculated was staggeringly low. It wasn't 0.04, it was closer to 0. 0.1, perhaps even lower. This object was one of the darkest things humanity had ever observed. It was blacker than fresh asphalt, blacker than coal, blacker than any known comet or asteroid in our cosmic neighborhood. It was a piece of the void itself, a moving patch of darkness. This discovery presented a profound physical problem. What could possibly make an object so incredibly dark? One theory was that it was coated in a complex web of Tholin's reddish-brown organic polymers formed by ultraviolet radiation, acting on simpler compounds like methane and FeVO and ethane. We see these substances on distant objects in our own Kuiper belt, but even those distant frozen worlds are not times this times dark. This was something else entirely. It was as if this interstellar traveller had been deliberately engineered to absorb light to move unseen through the galaxy. The mystery was no longer just about its lack of activity, it was now about its very substance. What alien chemistry could produce such a profoundly light-absorbing material? What environment could forge an object that drinks in the light of stars, giving almost nothing back? The story should have stalled there, leaving us with a perplexing but static puzzle. A dark, inert rock from another star. But the final piece of observational evidence, the one that would transform this mystery into a full-blown crisis of cosmic physics, was yet to come. It required us to look at 3I, Atlas, not in the light it reflected, but in the light it times emitted asterisk. Every object that absorbs energy must heat up, and anything with a temperature above absolute zero glows not necessarily in visible light, but in the infrared spectrum. Heat itself is a form of light. By turning infrared telescopes toward 3ITLAS, we could take its temperature. This measurement would be the ultimate arbiter. The logic was inescapable. An object this dark, absorbing over 99% of the solar energy striking its surface, must get warm. We could build precise models calculating exactly how hot it should be at its specific distance from the Sun, based on its size and its near-zero albedo. It was a straightforward calculation, a simple energy-in, energy-out balance. The Atacama Large Millimeter Array, a sprawling network of radio telescopes high in the Chilean desert, was tasked with this crucial observation. It stared at the object, collecting the faint thermal radiation, the whisper of heat traveling across hundreds of millions of miles. The data was collected, correlated, and analyzed. And when the final temperature reading was calculated, it sent a shockwave through the entire field of planetary science. The models had predicted a certain temperature, a number based on the fundamental laws of thermodynamics. But 3I, Atlas, was not obeying those laws. It was hot. Not just warm, but significantly, impossibly hotter than our models could account for. It was running a fever. This was the breaking point. This was the moment where every conventional explanation failed. The paradox was now complete and utterly terrifying in its implications. Here was an object that was refusing to sublimate its ices like a comet. Its lack of a coma meant that it wasn't using the sun's energy for that cooling process. Instead, its incredibly dark surface was absorbing that energy with terrifying efficiency. But that absorbed energy wasn't just passively re-radiating back into space as heat in a predictable way. The thermal excess was profound. It was soaking up sunlight like a sponge, and that energy was being trapped, stored, or converted in a way that was elevating its temperature far beyond the expected equilibrium. It was behaving like a cosmic heatsink, a celestial battery charging itself on the fires of our Sunday. The clash between expectation and reality could not have been more stark. We had a list of everything a comet should be, a behavioral profile, built on centuries of observation. 3I, Atlas, violated every single point. It should have been active. It was inert. It should have had a rich chemical spectrum. It was hauntingly featureless. It should have been dirty snowball dark. It was unnaturally, impossibly black. And most critically, it should have been using solar energy to power its outgassing, keeping its nucleus relatively cool. Instead, it was hoarding that energy, producing a thermal signature that screamed of an unknown physical process at work. The scientific community was in turmoil. The initial excitement of discovering an interstellar visitor had given way to a profound and humbling confusion. The object in our telescopes was not just an alien rock, it was an alien times idea asterisk. It refused to fit into any box we had built for it. It was a puzzle where every single piece was the wrong shape. We were not just observing a celestial body. We were being confronted by a phenomenon that seemed to defy our understanding of matter and energy. The quiet, unassuming smudge of light had become the solar system's most profound enigma. The question was no longer simply, what is it made of? It had become something far more fundamental, something that cut to the very heart of our assumptions about the universe. What times is this thing, and what in the cosmos is it doing? The silence that followed the confirmation was not one of peace. It was the heavy, pressurized silence of a submarine deep beneath the waves, the kind that descends after the hull groans under a force it was never built to withstand. Around the globe, in data centers and university offices, astronomers stared at the same impossible numbers. The error bars had vanished, the statistical noise had been filtered away, and what remained was a truth so stark, so contrary to expectation, that it felt like a violation. 3I, Atlas, was not reflecting the light of our sun. It was drinking it. It was a void, a moving patch of night cutting its way through a cosmos defined by light. The initial shock quickly gave way to a frantic global scramble for answers. This was no longer a routine observation of a peculiar interstellar guest. It had become a crisis of cosmic context, a direct challenge to our understanding of what can and cannot drift between the stars. The established catalogues of celestial objects, our carefully constructed taxonomies of comets, asteroids and planetesimals, were suddenly and violently rendered incomplete. There was a category missing, a type of object for which we had no name, no theory, no precedent. Emails flew across time zones at the speed of light, carrying with them fragments of code, spectral analyses, and increasingly desperate speculations. Video calls connected minds in Pasadena, Munich, and Tokyo, their faces illuminated by screens displaying the same deepening enigma. The object's trajectory was certain, its interstellar origin undeniable. But its substance, its very nature, had dissolved into a profound and unsettling question mark. Every telescope capable of observing it was commandeered, their schedules wiped clean to focus on this one aberrant point of darkness. We were throwing the combined power of human observation at a ghost. From this crucible of intense intellectual pressure, the first coherent hypotheses began to emerge, each an attempt to explain the inexplicable to fit this square peg into the round hole of known physics. The most conservative, the most grounded of these ideas was also perhaps the most primal. It proposed an object of profound and almost absolute blackness, a body forged from the one element that forms the very backbone of life as we know it, carbon. But this wasn't the carbon of diamonds or of living cells. This was carbon in its most elemental, light-devouring form, an object less like a rock and more like a celestial soot ball. Imagine, if you will, a star far older and more massive than our own one, that has reached the final convulsive stages of its existence. In its death throes, it swells into a red giant, its outer layers churning with elements forged in its core. This is a carbon star, a celestial furnace whose atmosphere is thick with carbon-based molecules, a dusky, smoky veil that shrouds its dying light. Within this stellar crucible, under conditions of immense heat and pressure, simple carbon atoms could link together into vast, complex fractal chains. They would form a cosmic smog of tholins and polycyclic aromatic hydrocarbons, sticky tar-like substances that are among the darkest materials known to science. This is the same kind of chemistry we suspect paints the hazy skies of Saturn's moon Titan, but magnified on a stellar, almost unimaginable scale. Now picture a cataclysmic event, a final helium flash or a violent stellar wind that blasts these atmospheric layers out into the interstellar void. Vast clouds of this dark, carbonaceous material would be ejected, cooling and condensing over millions of years as they drifted through the galactic dark. Clumps would form, sticking together not through the clean, crystalline bonds of ice, but through the messy, tangled adhesion of cosmic tar. The result would be an object born of stellar ash, a remnant of a dead star's final smoky breath. It would be a traveller made of almost pure, unadulterated soot, its surface, a microscopic landscape of jagged interlocking carbon molecules, a perfect light trap on a planetary scale. When photons from our sun strike such a surface, they don't bounce. There is no smooth reflective plane to send them back into space. Instead, they plunge into a forest of carbon, bouncing from one molecule to the next, their energy being absorbed and converted into imperceptible heat with every single impact. The light checks in, but it never checks out. The object would possess an albedo, a measure of reflectivity so low it would barely register. It would be darker than fresh asphalt, blacker than coal, a solid fragment of the void itself. This soot ball hypothesis was elegant. It used known elements, known stellar processes, and it provided a direct physical mechanism for the extreme absorption we were witnessing. It painted a picture of a universe that recycles its dead sending, fragments of stellar cinders like cosmic mourners on billion-year journeys to visit other suns. It suggested 3i. Atlas was not an alien, but a relative of sorts forged from the same elemental dust that would eventually form planets and people. Yet, for all its elegance, a deep sense of unease remained. The level of absorption was at the absolute extreme end of what even this theory could predict. Could an object so purely and uniformly carbonaceous even form? Wouldn't it be contaminated by silicates, by ices, by the other elements swirling in its parent star's atmosphere? And could such a loosely aggregated ball of soot, survive the brutal radiation and gravitational stresses of interstellar travel. It felt like a plausible explanation, but a strained one pushing the boundaries of what we thought was possible. The universe is rarely so perfectly pure. This doubt opened the door for a second, even more exotic idea. What if the darkness of 3I, Atlas, wasn't about its composition but its construction? What if the object wasn't a solid ball of soot but something far stranger, something almost ethereal, a body composed more of empty space than of matter? This was the cosmic fairy castle hypothesis, the theory of the fluffy aggregate. It proposed that 3I, Atlas, had a structure of unimaginable porosity, a ghostly architecture that was less a solid object and more of a three-dimensional web. To understand this, you have to journey far from the violent heart of a dying star, out into the coldest, quietest, most desolate regions of the galaxy, the heart of a dense molecular cloud. Here in the interstellar twilight, temperatures hover just a few degrees above absolute zero. There is no turbulence, no stellar wind, just a profound and patient stillness that can last for eons. In this cosmic sanctuary, microscopic grains of dust and ice, the seeds of future worlds begin to drift toward one another under the almost imperceptible pull of their mutual gravity. They don't collide. They don't smash together. They touch gently and stick, bound by faint electrostatic forces. Another grain joins, then another, and another over millions upon millions of years. The structure that grows is not a solid, compacted snowball. It is a fractal labyrinth, a delicate branching filigree of ice and dust, like a snowflake grown to the size of a mountain. Its density would be absurdly low, perhaps less than that of the air you are breathing right now. It would be a solid, yes, but a solid that is 99.9% empty space. We have a name for a man-made material with similar properties, aerogel or frozen smoke. 3I, Atlas, this theory suggested, was a natural celestial aerogel of incomprehensible scale. Now, when a ray of sunlight strikes this phantom object, it doesn't see a surface. It penetrates, entering a crystalline maze of ice and dust. The photon is not reflected back towards our telescopes. It is scattered inward deeper and deeper into the object's porous heart. It ricochets through the translucent structure its path, a chaotic pinball game within a crystal cage. With each microscopic collision, it loses a tiny bit of its energy, its light dimming as it's converted into vibrational heat within the object's fragile lattice. The light is not so much absorbed by the material as it is trapped by the architecture. It becomes lost within a ghost wandering an endless hall of mirrors until its energy is fully spent. This object would appear black not because it was made of dark material, but because it was a perfect trap, an intricate cage for light from which there was no escape. This hypothesis was deeply compelling because it explained not only the darkness, but also some of the other subtle anomalies that were beginning to appear in the data. Faint, almost undetectable outgassing was occurring without the bright coma of a typical comet, something that could be explained by sunlight, slowly warming ices buried deep within the porous interior. It painted 3I, Atlas, as a pristine artifact, a survivor from the very dawn of another solar system, a fluffy, uncompressed piece of the original nebula from which its homeworlds were born. It was a sample of another creation story delivered to our doorstep. But the problem of its journey remained magnified 1,000 times over. How could something so impossibly delicate, a structure more fragile than spun sugar, survive being ejected from its home system? How could it withstand the relentless bombardment of cosmic rays, the tidal forces of passing stars, and the gravitational stresses of its final searing approach to our own sun? It seemed a contradiction in terms, an object strong enough to cross the interstellar abyss, yet so fragile it could be crushed in your hand. The cosmic fairy castle was a beautiful, elegant theory, but it seemed destined to shatter against the harsh reality of the void. And so, with the leading explanations both strained to their breaking points, a third, more unsettling possibility began to be whispered on late-night forums and in hushed conversations. It was a hypothesis born of humility and of awe, an admission that perhaps the box we were trying to fit this object into was simply too small. Perhaps the problem wasn't with our theories of carbon or of aggregation. Perhaps the problem was with our fundamental assumptions about matter itself. This was the threshold of the truly unknown, the idea that 3I, Atlas, was not just an unusual rock but a completely novel form of object, something for which our terrestrial and solar system-based experience had left us, utterly unprepared. We build our understanding of the universe on what we can see and what we can create in our labs. Our physics and chemistry are by necessity local. They are based on the conditions prevalent in our corner of the Milky Way around a G-type main sequence star on a rocky planet with a specific gravity and atmospheric pressure. But what kind of matter might form in the truly extreme corners of the cosmos? What substances could be forged in the crushing gravity of a neutron star's crust, where the pressure is so immense that the very structure of atoms is warped into something we can barely conceive of, a kind of nuclear pasta? What unique crystalline structures or metallic alloys might condense out of the superheated plasma swirling in the accretion disk of a black hole? A place where magnetic fields can contort the laws of chemistry. Could there be stable allotropes of common elements, exotic arrangements of atoms that are only possible under temperatures and pressures we have never been able to replicate? This third path suggested that 3I, Atlas, was a messenger from one of these cosmic extremes. It wasn't made of soot or of ice. It was a shard of impossible physics. Its material might possess quantum properties that allow for near-perfect energy absorption across the entire electromagnetic spectrum. It could have a surface engineered at the atomic level not by intelligence, but by the relentless, unimaginable physics of its birthplace to be a perfect energy sink. We were trying to understand it by comparing it to coal and to ice, which was like an ancient Roman trying to understand a microchip by comparing it to clay and to papyrus. The fundamental principles were simply from a different universe of experience. This was no longer a problem of astronomy. It was a challenge to fundamental physics. It implied that the periodic table as we know it might just be a single chapter in a much larger encyclopedia of matter. It meant that out there in the vastness between the stars were not just different worlds, but different ways of being. This object wasn't just a visitor. It was a revelation, a physical artifact proving that the universe is not only stranger than we imagine, but stranger than we can times imagine. It was a piece of evidence for a cosmos more varied, more complex, and more mysterious than we had ever dared to believe. The three hypotheses stood in stark contrast: a cinder from a dead star, a ghost from a nascent one, or a relic from a realm of physics beyond our comprehension. Each carried with it profound implications for our place in the cosmos. And as 3I, Atlas continued its silent, inexorable journey through our solar system, it held the answer to its true nature locked deep within its lightless heart. The frantic search for explanations had reached its limit. Observation and theory had taken us as far as they could. The object was no longer just a puzzle. It had become the ultimate test. To solve it, we would have to do more than just watch. We would have to get closer, much, much closer. And so, with our catalogue of possibilities laid before us, the real work began. The theories spun from the brilliant minds of planetary scientists were elegant, compelling, and for the moment pure speculation. They were ghosts in the machine, phantoms of physics and chemistry that might explain the unholy darkness of 3I, Atlas. But science does not trade in ghosts for long. It demands evidence, a reckoning. To find it, we had to turn our global network of observatories into a grand interrogation room, placing this silent traveller in a virtual witness stand millions of miles away. We couldn't collect a sample, we couldn't land a probe not on an object moving with such blistering speed. Our only tools were the ancient messengers of the cosmos. The photons of light that had travelled from the sun touched the surface of this enigma and then made the long, lonely journey back to us. Every single photon that reached our telescopes was a potential clue, a survivor of an encounter that had consumed nearly all of its brethren. Our task was to capture these few survivors and force them to tell their story. The primary method in this cosmic cross-examination is a technique of breathtaking elegant spectroscopy. Think of it as putting light through a prism, but one of immense power and precision. When sunlight, which contains a full rainbow of colours, strikes an object, the atoms and molecules on its surface absorb very specific frequencies, specific shades of colour based on their unique quantum structures. The light that bounces back to us is therefore missing these colors. It arrives with a pattern of black lines carved out of its spectrum, a chemical barcode that screams the identity of the materials present. It is the single most powerful tool we have for understanding the composition of distant worlds. With it, we have tasted the atmospheres of planets orbiting other stars and mapped the mineral wealth of asteroids. For 3I Atlas, the hope was that this barcode would be clear and unambiguous. If its surface was rich in complex hydrocarbons, we would see the telltale absorption bands of carbon-hydrogen bonds. If it were covered in the exotic reddish tholins born in the outer solar system, its spectrum would have a distinct sloping signature. We aimed our most powerful spectrographs instruments cooled to near absolute zero to detect the faintest signals, and we waited. The initial data that trickled in was frustrating. It was noisy, a faint whisper against the background hiss of the universe, a challenge born from the object's immense distance and its profound darkness. Teams around the world spent weeks, then months stacking images digitally, combining exposures to build up a stronger and stronger signal, filtering out the random noise to reveal the true message hidden within. As the picture slowly sharpened, a collective sense of disbelief began to ripple through the astronomical community. The spectral barcode we had hoped for simply wasn't there. There were no deep, clear absorption lines, no distinctive curves, no chemical fingerprints to latch onto. Instead, the spectrum was hauntingly, unnervingly flat. From the deep violet to the far infrared 3I, Atlas was absorbing light with almost uniform efficiency. It was a perfect, featureless void. This was not the signature of a simple carbon-rich asteroid, nor did it perfectly match the tholins we've observed on objects like Arakoth. A flat spectrum implies a substance or a mixture of substances so complex and disordered that it swallows all light indiscriminately. It was like interrogating a suspect who refused to speak, whose expression never changed, revealing nothing. The darkness itself was the only message, and the absence of features became the most terrifying feature of all. It ruled out simple chemical explanations and forced us to consider that the answer might not lie in what times the object was made of, but in its physical form. This pushed us toward our second tool, a far more subtle art called polarimetry. While spectroscopy tells you what a material is, polarimetry can tell you what its time's like, asterisk. Light from the sun is unpolarized, meaning its waves vibrate in all directions randomly. But when this light bounces off a surface, it becomes partially polarized. The reflected waves tend to vibrate more in one direction than in others. Imagine skipping a stone across a lake. The stone itself is the photon, and the way it bounces the angle, and the splash tells you about the surface of the water. A smooth, glassy surface, like a calm lake, polarizes light in a very predictable way. A rough, jagged surface creates a much more chaotic, weakly polarized signal. And an extremely porous surface, one made of incredibly fine, loosely packed grains, does something very strange indeed. It can create a phenomenon called negative polarization at certain viewing angles, a bizarre optical quirk that is a hallmark of what astronomers call a regolith, a layer of fine dust and rubble. This was our chance to test the fairy castle hypothesis, the idea that 3I Atlas wasn't a solid body but a delicate fractal-like aggregation of dust whose intricate structure was the perfect light trap. The measurement is excruciatingly difficult. You are trying to detect a tiny preference in the vibration of light from an object that is barely reflecting any light at all. It is like trying to discern the texture of a black cat in a coal cellar by the glint in its eye. The world's largest telescopes had to stare at 3I Atlas for hours on end, their instruments painstakingly measuring the orientation of every photon they could catch. The results, when they finally came, were a thunderclap. The degree of polarization was unlike almost anything we had ever seen. It strongly suggested a surface covered in a regolith of extraordinarily fine particles, far smaller than the grains of sand on a beach, perhaps as fine as smoke or soot. The data was a near-perfect match for a surface with a porosity exceeding 80 or even 90%. This was not a rock, it was a cosmic dust bunny, a clump of celestial fluff so delicate that it seemed impossible it could even hold itself together. The fairy castle structure, once a fringe idea, was now a leading contender. The object's profound darkness wasn't just chemical, it was structural. Light that entered the porous labyrinth didn't just hit one surface. It bounced between countless tiny grains, losing a little more energy with each reflection until it was completely absorbed. It checked out. But it also opened a terrifying new question. How could a structure so fragile, more void than substance, possibly survive the gravitational stresses and solar radiation of a journey through the heart of the solar system? It was an object that, by all rights, should have disintegrated. There was a third test, a third angle of attack. If 3I, Atlas, was absorbing nearly all the solar energy that hit it, that energy had to go somewhere. The laws of thermodynamics are absolute. Energy cannot be destroyed. It was being converted into heat. This meant the object, despite its distance from the sun, should be warmer than a more reflective body at the same orbit. We could take its temperature. Using powerful infrared telescopes which see heat rather than visible light, we could measure the faint thermal glow emanating from its surface. This measurement of its thermal inertia would provide another crucial clue to its structure. Think of the difference between pavement and sand on a hot day. The dark pavement, a solid material with high thermal inertia, absorbs sunlight all day and stays hot long into the evening. The bright sand with lower thermal inertia heats up quickly but also cools down almost instantly once the sun sets. By watching how 3I, Atlas's, temperature changed as it rotated as different parts of its surface were exposed to sunlight and then turned into the cold darkness of space, we could determine if it was behaving like a solid rock or a fluffy insulator. Once again, the technical challenge was immense. We were searching for the heat signature of a small, distant object against the cold backdrop of deep space, the equivalent of trying to spot a warm ember from 100 miles away. Space-based observatories like the Spitzer Space Telescope before its mission ended and the Neowise mission were repurposed to stare at the coordinates where Atlas was predicted to be patiently gathering the faint infrared photons that were the ghostly echo of its absorbed sunlight. The data that emerged was yet another piece of the deepening enigma. The object's thermal inertia was astonishingly low. It shed heat almost instantly. The moment a part of its surface rotated out of direct sunlight, its temperature plummeted. This was not the behavior of a solid, coherent rock. A solid body, even a dark one, would retain some heat glowing faintly on its night side. 3I Atlas did not. It behaved like a perfect insulator, a structure so porous that heat could not effectively conduct from the surface into the interior. It was as if only the very top microscopic layer of dust was heating up a thin skin of warmth on an eternally frozen body. This result dovetailed perfectly with the polarimetry data. Both lines of evidence were pointing away from a solid object and toward a bizarre, ultra-porous aggregate. With this strange portfolio of data in hand, a featureless spectrum, extreme polarization, and low thermal inertia, it was time to search for a precedent. We had to comb through our vast celestial library to see if anything we knew matched this baffling profile. The process began in our own backyard with the main asteroid belt. Here we find the C-type or carbonaceous asteroids. They are among the darkest objects in the solar system, primitive relics rich in carbon and water. On paper, they were a prime suspect. We pulled up their spectral data, their polarization curves, their thermal models, and while there were similarities, the match was imperfect. The darkest C-type asteroids have an albedo, a measure of reflectivity of around 3 to 5%. 3I, Atlas, was darker still. Their spectra, while subdued, still showed faint bumps and wiggles, the ghostly fingerprints of water-bearing clay minerals. The spectrum of Atlas was a flat line. They were close cousins perhaps, but 3I, Atlas, was the family's inscrutable silent outlier. So we looked to the comets. A comet's nucleus, after many passages near the sun, can build up a thick crust of dark organic material as its more volatile ices are boiled away. The nucleus of Halley's Comet, for instance, is famously one of the darkest objects known blacker than coal. This devolatilized mantle could theoretically explain the color. But a comet, even a dormant one, carries its history with it. Under the intense heat of the sun, where Atlas was traveling, any remaining subsurface ices should have been stirred producing at least a faint coma of outgassing a whisper of a tale. We watched 3I, Atlas, with fanatical attention searching for any hint of such activity. There was none. It was completely, utterly inert. It had the dark crust of an ancient comet, but without the frozen heart. It was a ghost ship, silent and dead, showing no signs of the icy life that defines its kind. This path of inquiry led only to another dead end, another beautiful theory slain by an inconvenient fact. The search moved outwards to the cold, distant frontiers of our solar system, to the Kuiper Belt. Here, beyond the orbit of Neptune, drift countless primordial bodies preserved in a deep freeze since the dawn of the solar system. These Kuiper Belt objects, or KBOs, are known to be coated in a complex sludge of organic molecules called tholins. These materials are created over billions of years, as faint ultraviolet light from the distant sun and cosmic rays cook the simple ichs of methane, nitrogen, and ammonia, forging them into complex carbon-rich polymers. Tholins are famously dark and often have a reddish hue, and their spectra can be relatively featureless. An object like Arakoth, visited by the New Horizons spacecraft, gave us our first close-up look at such a world. Could 3I, Atlas, be one of these bodies, a refugee from the outer darkness kicked from its stable orbit and sent on a long plunge toward the sun? This was by far the most promising analogy. The extreme darkness, the potential for an organic-rich surface, it all seemed to fit. This hypothesis gained tentative support throughout the scientific teams. Yet even here, the puzzle was not perfectly solved. Most KBOs we've studied have a distinct reddish colour, a product of their specific tholin chemistry. 3I, Atlas, was neutrally dark, black, not red-black. It was as if it were coated in a different kind of tholin, one forged under unknown conditions, or perhaps something else entirely. It was an extreme version of a KBO, an outlier even among outliers. When direct observation and comparison proved insufficient, the investigation moved into the digital realm. Scientists built 3I, Atlas, inside supercomputers, creating virtual models to test the competing ideas. They could construct an object atom by atom, molecule by molecule, and then shine a simulated sun upon it. One team built a model of a solid body made of amorphous carbon, like a giant piece of charcoal. Another built a model based on the fairy castle idea, a fractal aggregate of trillions of tiny tholin-coated dust grains. They let the virtual photons fly. In these simulations, they could track every bounce, every absorption, every reflection. They could calculate the exact spectrum, the precise polarization, and the thermal glow their virtual object would produce. Then they would compare the simulation's output to the real hard-won data from the telescopes. It became a painstaking process of trial and error. The solid carbon model failed. It reflected too much light at certain wavelengths. A simple coating of known tholins on a solid core also failed. It couldn't reproduce the extreme negative polarization. The models that came closest, the ones that began to eerily echo the observed reality, were the most complex. They required a surface of mind-boggling porosity, composed of incredibly small, highly absorbent grains. The simulations that worked best suggested a structure more fragile than spun sugar, a chaotic mesh of carbon-rich particles that was almost entirely empty space. The pieces were beginning to align, but they weren't forming a picture of resolution. They were creating a portrait of something profoundly strange, a paradox given physical form. We had started with a simple question: why is this object so dark? And now we had a tentative, terrifying answer. It's dark because it is practically nothing at all. It appears to be a loosely bound collection of fine, dark dust, so porous and delicate that it operates as a perfect light trap. But this answer was more unsettling than the original question. It traded a mystery of chemistry for a mystery of physics. Our investigation had methodically peeled back the outer layers of the problem, ruling out simple asteroids and comets, only to reveal a core that made even less sense. The data no longer pointed to a familiar geological object. It pointed to a structure, a material that sits at the very edge of our understanding. The question was no longer just about its composition. The question was now about its very existence. How could such an impossibly fragile object form, and how could it possibly survive its violent journey through space? We had followed the evidence, and it had led us to the precipice of a much deeper, more fundamental mystery, and so we were left adrift in a sea of contradictions. Adrift with a ghost from another star, an object that refused every label we tried to place upon it. It was too dark to be a common asteroid, too quiet to be an active comet. It drank in the fierce light of our sun, not with the passive indifference of rock, but with an insatiable, almost biological thirst. The data streamed back from our most powerful telescopes painted a portrait of an impossibility, a celestial refugee that played by rules we had not yet written. Every theory we posed, every model we built, shattered against the stark reality of its existence. We had exhausted the familiar catalogues of the cosmos, and 3I, Atlas, remained a singular, defiant enigma. The breakthrough, when it finally arrived, was not a sudden flash of insight from a single new discovery. It was slower, more profound. It was the quiet convergence of scattered evidence, the dissonant notes of data from a dozen different instruments suddenly resolving into a strange and beautiful chord. Teams across the globe who had been staring at isolated pieces of the puzzle, its faint reddish hue, its extreme lack of reflectivity, its bizarre thermal signature, began to superimpose their findings. They stopped asking what times, single thing times is this object, and started asking a much more powerful question. What times, sequence of events, times what epic journey could forge such a creature? The answer that began to emerge was not about an object but a biography. Let's return to the first, most subtle clue. Hidden beneath its overwhelming darkness was a faint, almost imperceptible reddish tint, a spectral whisper picked up only by the most sensitive spectrographs. For months it was dismissed as noise, an instrumental artifact. But as the data accumulated, the whisper became a persistent, undeniable voice, and it spoke of chemistry. Not the simple chemistry of silicon and iron that makes up our asteroids, but something far more complex, far more organic. The color was a spectral match for a family of substances that we until now had only encountered in two very specific places in the laboratory, flasks of scientists trying to recreate the origins of life, and in the thick, hazy atmosphere of Saturn's moon Titan. They are known by a name coined by Carl Sagan himself, tholins. Tholins are not a single molecule, but a vast, tangled ecosystem of complex organic compounds. Imagine the primordial soup of a young solar system, rich in simple molecules like methane, ammonia, and nitrogen. Now bathe that soup in the high-energy ultraviolet radiation from a young, violent star. This celestial blowtorch shatters the simple molecules, and their fragments, reactive and energetic, recombine in ever more complex ways. They link together, forming long, sticky chains and rings of carbon, hydrogen, and nitrogen. This process, repeated over millennia, creates a reddish-brown, tar-like substance, a cosmic sludge that coats the surfaces of fledgling worlds and icy bodies. It's the universe's raw pigment, the stuff from which the building blocks of biology might one day emerge. On Titan, these tholins rain down from the orange sky, coating the moon in organic dunes. In the lab, they are the very substances that, when mixed with water, can produce amino acids, the fundamental components of proteins. Finding their chemical signature on 3I, Atlas was electrifying. It told us that this wanderer was born in a place chemically alive, a stellar nursery brimming with the same raw ingredients that may have seeded life on our own planet. It was not a dead piece of rock, but a frozen chemical factory, a time capsule from a distant fertile genesis. This was a monumental discovery in its own right, a tangible link to the chemistry of another star system. But it also deepened the mystery. Tholins are reddish, yes, but they are not times this, times dark. They are not the light-devouring abyss we observed. The first piece of the biography was in place, the story of its birth, but something must have happened on its long journey, something that profoundly changed it. This is where the second line of evidence comes into play, the sheer oppressive blackness of the object. Its albedo, the measure of its reflectivity, was lower than fresh asphalt, darker than coal dust. This wasn't just a surface that was poor at reflecting light. It was a surface that seemed engineered to destroy it. To understand how such a thing could be made, we had to consider the environment 3I Atlas had inhabited for perhaps hundreds of millions of years. Not the warm, protected cradle of a solar system, but the vast, lethal emptiness between the stars. Interstellar space is not truly empty. It is filled with a relentless, invisible rain of high-energy particles, a spray of protons and atomic nuclei, accelerated to near the speed of light by ancient supernovae and the churning hearts of distant galaxies. This is the hailstorm of galactic cosmic rays. For an object like 3I, Atlas, traversing this void for eons, this cosmic radiation is a transformative force. It is a form of cosmic sandpaper, a slow-motion fire that scours and re-engineers its very surface. Each high-energy particle that strikes the object is like a microscopic cannonball slamming into the complex tholin molecules. It doesn't just chip away at the surface, it triggers a cascade of chemical reactions. It shatters weaker chemical bonds and provides the energy for new, more resilient ones to form. This process, a hyper-accelerated version of what we call space weathering in our own solar system, systematically breaks down the organic sludge. The lighter elements like hydrogen are gradually blasted away into space. What's left behind is a progressively more concentrated network of carbon. You are watching a process of slow cosmic carbonization. Over millions of years, the relentless particle bombardment cooked the reddish tholins, darkening them, polymerizing them into a complex cross-linked carbon-rich crust. Think of it as leaving bread in a toaster for 1,000,000 years. It goes from golden brown to charcoal black. The reddish signature of the fresh tholins doesn't vanish entirely. It's still there, buried just beneath the surface, a palimpsest of its youth. But the outermost layer becomes a different beast altogether. An intricate blackened lattice of carbon, almost fractal in its complexity, exceptionally good at trapping any photon that dares to touch it. This cosmic ray baking perfectly explained the object's profound darkness. It was the second chapter of its biography, a long, lonely and transformative adolescence spent wandering the galactic wilderness. We now had a chemically rich origin and a brutal interstellar journey. The picture was becoming clearer, but one stubborn paradox remained. The thermal data, our measurements showed that 3I, Atlas, was absorbing an enormous amount of solar energy, getting far warmer than a typical asteroid at its distance. Yet it wasn't re-radiating that heat back into space in the way a solid, rocky object should. The heat was getting times in times, but it wasn't getting times out times efficiently. This suggested the object's darkness wasn't just skin deep, it was structural. It wasn't just about the material it was made of, but the way that material was put together. The final key came from modeling the very first moments of planet formation in the cold, tenuous dust clouds that swirl around newborn stars. In these environments, objects don't form by molten rock crashing together. They grow through a gentle, almost hesitant process of accretion. Tiny, fluffy dust grains coated in ice and organic tholins bump into each other and stick held together by faint electrostatic forces. They don't compact into a solid sphere. Instead, they build up like snowflakes, creating an incredibly delicate, porous and intricate structure. Imagine a celestial fairy castle or a sponge made of soot. This is what we call a fractal aggregate or a cometary rubble pile. It is an object that is mostly empty space, a loose scaffolding of grains with vast microscopic caverns and tunnels in between. And this structure, it turns out, is the most perfect light trap nature can build. When a photon of sunlight strikes the surface of a solid rock, it has two choices. It can be reflected away, or it can be absorbed by the surface, heating it up. But when a photon strikes the surface of an object like 3I, Atlas, it enters a labyrinth. It doesn't just hit a single surface, it plunges into the porous network. It might bounce off one grain only to be sent deeper into the structure, where it hits another and another and another. With each bounce, it loses a little bit of its energy, converting it to heat. The chances of it finding its way back out to be reflected into space are infinitesimally small. The light is caught, trapped, and its energy is absorbed deep within the object's structure. This explains the thermal paradox. The energy is deposited not just on the surface but within the top layers of the object, and its incredibly low density and lack of solid connections make it a terrible thermal conductor. The heat stays trapped inside, struggling to escape. This was the final chapter of its physical story, the tale of its gentle, fragile construction. And there it was, the grand synthesis. The solution was not one thing but a triumvirate of processes, a perfect storm of cosmic phenomena that worked in concert to create this beautiful monster. You start in a distant, nascent solar system, one rich in organic chemistry, and you gently accrete tholin-coated dust grains into a fragile, hyperporous body. You create an object that is from its very inception a structural light trap. Then you eject this fledgling world from the gravity of its parent star. You send it on a journey across the galaxy that lasts for hundreds of millions of years, and all along that journey you bombard it with the relentless fury of galactic cosmic rays, which bake its organic-rich surface, transforming the reddish tholins into a blackened, carbonized crust that is itself almost perfectly absorbent. You have now created 3I Atlas. The unique color, the extreme darkness, the anomalous thermal properties, all three mysteries which had seemed so contradictory were now resolved by a single, elegant, and breathtakingly epic narrative. It was a revelation that sent shockwaves through the astronomical community, because in solving the riddle of this one object, we had inadvertently opened a window into the breathtaking diversity of the galaxy. We had always assumed, with a kind of cosmic provincialism, that visitors from other stars would be more or less like the objects we knew, comets from our Oort cloud, asteroids from our belt. We assumed a universal standard for planetary construction. 3I Atlas shattered that assumption into a million pieces. This was not just another rock, this was evidence. Evidence that other stellar nurseries have their own unique chemical thumbprints, some far richer in the precursors to life than our own was. Evidence that the process of planetary formation can produce architectures, these incredibly fragile, low-density bodies that may be common elsewhere but are rare in our own cosmic neighborhood. It tells us that the galaxy is filled not with copies of our solar system, but with an endless variety of alternatives, each shaped by its own star, its own chemistry, its own history. 3I Atlas was a messenger, and its message was clear: the universe has a far richer architectural palette, a much more creative and surprising imagination than we ever dared to believe. We had been looking for cousins, and instead we found something wonderfully, beautifully alien. The question was no longer simply what 3I Atlas times was times, but how many more of these silent dark messengers were drifting toward us, each carrying the secret history of its own lost sun. The hunt had just begun, and so the spectre that had haunted our telescopes, this ghost of pure darkness, finally began to resolve into something tangible. The final pieces of the puzzle, painstakingly gathered from faint signatures of scattered light and subtle gravitational nudges, clicked into place, not with a triumphant shout, but with a quiet, collective intake of breath across the astronomical community. The shadow crossing our sun, the interstellar enigma we called 3I Atlas, was not a rock. It was not a conventional comet shrouded in a familiar veil of ice and dust. It was something far stranger, a concept pulled from the very edge of theoretical physics and given solid, albeit ephemeral form. We had been searching for a key, expecting something forged of metal or stone, only to find the lock was opened by a key made of frozen smoke. Our journey with this phantom began with a simple, maddening observation, an object that absorbed nearly every photon of sunlight that fell upon it. In a solar system filled with reflective bodies, from the brilliant ice of Enceladus to the dusty red plains of Mars, 3I Atlas was a void. It was a patch of utter blackness against the tapestry of space, a hole in the cosmic fabric. Initial theories, as we've seen, were born from our own limited experience. Perhaps it was coated in a complex carbon soot, a residue of some distant, violent stellar event. Maybe it was a slag heap from an alien industrial process, a piece of cosmic debris with a technological origin. We threw every model we had at the problem, from exotic metallic compositions to bizarre magnetic field interactions, and every single one failed. The data stubbornly refused to conform to our expectations, whispering that we were not just wrong, but that our entire frame of reference was insufficient. We were like ancient cartographers trying to map an entire new continent using only the landmarks of their home village. The scale of our ignorance was becoming the most significant discovery of all. The breakthrough, as it so often does, came not from a single observation, but from the synthesis of dozens of seemingly unrelated data points. The slight, almost imperceptible outgassing of noble gases detected only at the very limits of our spectroscopic capabilities hinted at an object that was not just cold, but had been formed in a place of truly profound coldness. The way it failed to fragment under the sun's tidal forces, despite having a density less than that of cork, suggested a structure that was not a solid monolith. It pointed to something more akin to a sponge or a fractal network possessing immense tensile strength through its intricate interconnected geometry. This was the cosmic equivalent of aerogel, a structure composed of more than 99% empty space, yet coherent and stable. It was a celestial snowflake writ large on a scale of kilometers, its complex arms and branches perfectly designed to trap light to draw it in and extinguish it within its labyrinthine depths. A light trap drifting between the stars. What you have witnessed is the birth of a new cosmic category. Before this visitor, our understanding of planetary building blocks was defined by the asteroids and comets of our own solar system. We had the rocky, dense asteroids of the inner belt relics of a warmer, more violent youth. We had the icy, volatile comets of the Kuiper Belt and the Oort cloud, pristine time capsules from the solar system's frigid outer margins. These were our two primary archetypes, the foundational ingredients from which we believed all worlds were made. 3I, Atlas, has shattered that simple dichotomy. It has shown us that out there in the vast unexplored wilderness between the stars, nature's imagination is running wild. It is forging objects from materials and through processes we are only just beginning to comprehend. This dark wanderer is a testament to the sheer diversity of creation. Imagine the stellar nursery from which it was born. Not a turbulent, hot environment like our own sun's birthplace, but a truly immense, ancient and bone-chillingly cold molecular cloud. In this cosmic refrigerator, at temperatures just fractions of a degree above absolute zero, exotic chemical reactions impossible in our warmer neighborhood could proceed at a glacial pace over millions of years. Gases like methane and nitrogen, instead of forming a simple icy crust, could polymerize into long, complex organic chains, weaving themselves into a fluffy, porous matrix. This structure, a delicate filigree of frozen hydrocarbons and trapped noble gases, would grow like a crystal in supercooled water, expanding outward into a low-density, high-strength aggregate. It would be an object born of quiescence, a child of the deepest cold and darkest night. It tells us that some planetary systems may not begin with a barrage of rocky collisions, but with the gentle accumulation of these vast feather-light building blocks. Worlds could be born not in fire but in frost. This revelation forces us to look back at our own history with new eyes. How many other such objects have slipped through our celestial nets, their profound darkness rendering them all but invisible to surveys looking for points of light? We have been scanning the heavens for brilliant diamonds, and in doing so have missed the pieces of velvet coal floating silently past our window. We now understand that the interstellar medium is not just an empty void punctuated by the occasional rogue asteroid or comet. It is likely teeming with these dark pilgrims, a hidden population of matter that could fundamentally alter our estimates for the mass locked away between the stars. They may even be the primary delivery mechanism for complex organic molecules, the precursors to life-seeding nascent solar systems with the raw ingredients needed for biology. 3I, Atlas, was not just a curiosity. It was a messenger carrying a dark letter that has forced us to reread the entire story of cosmic evolution. Its discovery and the struggle to understand it will echo for decades in the way we conduct astronomy. The Vera C. Rubin Observatory, with its unprecedented ability to scan the entire visible sky every few nights, is now being programmed with new marching orders. Its algorithms will not just be searching for things that move or flash, but for things that are conspicuously absent. It will hunt for occultations, for the telltale stellar blinks caused by dark, unseen objects passing in front of distant stars. We are now, in essence, learning how to search for the shadows to map the universe, not just by its light, but by its absences. The James Webb Space Telescope, with its extraordinary sensitivity to the faint thermal glow of cold objects, can follow up on these detections, tasting the chemical composition of their minimal outgassing with a precision we could once only dream of. We are no longer just stargazers. We have become cosmic detectives looking for fingerprints on the darkness. Future telescopes, giant observatories, still on the drawing board, will be designed with this challenge in mind. They will be equipped with advanced coronagraphs and polarimeters, specifically engineered to detect the faint polarized sheen of starlight reflecting at a shallow angle from an ultra-dark surface. We are entering an era where we will build machines not to see the brightest objects in the cosmos, but to see the dimmest, to chase the faintest whispers from these interstellar ghosts. Every new detection of an object like 3I, Atlas, will be another crucial data point, another piece of a galactic puzzle. Are they all made of this porous organic material? Do they come in different shapes and sizes? Do they originate from specific types of star systems? Each one will be a celestial Rosetta Stone helping us to translate the language of a different corner of the galaxy, revealing the local chemistry and physics of its origin. And what of meeting one of these visitors up close? The profound challenge posed by 3I, Atlas, has sent ripples through the communities, designing the next generation of robotic explorers. Before we envisioned interstellar probes that would intercept solid rocky targets like Oumuamua, perhaps using harpoons or drills to take a sample. But how do you land on a craft made of what is essentially frozen smoke? How do you anchor a probe to a body with almost no structural integrity and negligible gravity? A conventional landing would be like trying to land a helicopter on a cloud. A drilling attempt might cause the entire object to instantly disintegrate into a puff of gas and dust. The encounter has ignited a revolution in mission design. Engineers are now contemplating entirely new classes of probes. Imagine a swarm mission, where a mothership releases dozens of tiny independent sensor probes that would fly in formation through the object's fragile structure, mapping its internal density and composition without ever making physical contact. We are envisioning net probes that could gently envelop a smaller fragment using electrostatic forces to hold it in place for analysis. Spectrometers are being redesigned to operate at cryogenic temperatures capable of analyzing materials that would vaporize upon contact with even the faintest warmth from a probe's electronics. We need to develop instruments that can perform a gentle, remote sort of touch, a way to understand the substance of a ghost without dispelling it. The legacy of 3I, Atlas, will be written in the blueprints of these audacious future missions, pushing our technology to the very brink of what is possible. It has provided us not with a destination, but with a new kind of navigational chart, one that points toward challenges we never even knew existed. This is why we explore. This is why we build these colossal eyes of glass and steel, and why we fling our robotic emissaries into the unforgiving void. We do it for moments precisely like this. The universe, in its infinite and humbling grandeur, does not always give us the answers we expect. It does not conform to the neat and tidy boxes we construct for it. Instead, it presents us with anomalies, with paradoxes, with objects of impossible darkness that defy our every preconception. And in doing so, it offers us a profound gift, the opportunity to be wrong, the chance to tear down our old comfortable ideas and build new ones that are grander, more inclusive, and more aligned with the staggering reality of what lies beyond our world. 3I, Atlas, did more than just fly through our solar system. It flew through the heart of our assumptions, leaving a trail of exhilarating questions in its wake. From a single puzzling point of light, or rather a puzzling lack of light, an entire new avenue of cosmic inquiry has been born. We have been reminded that the most profound discoveries are often not found in answering old questions, but in learning to ask entirely new ones. What else is out there drifting in the silent, patient darkness between the suns? What other forms of matter forged in alien crucibles are even now making their long journey toward our star? The journey to understand 3I, Atlas, has been a humbling, illuminating odyssey, a perfect microcosm of the scientific endeavor itself. It is a story of mystery, of frustration, of ingenuity, and ultimately of revelation. It is a story that confirms we are still in the dawn of our cosmic awareness, with an entire universe of wonders still waiting to be found, hiding in plain sight or perhaps in the deepest of shadows. The quest continues, not for a final definitive answer, but for the endless, beautiful, and transformative process of discovery itself. The darkness has spoken, and we are finally learning how to listen.